We just hold until maybe 5 before.
Ты ради себя.
Going. And that said, so tonight, again, my name is
We just hold until maybe 5 before.
I'm in Central New Jersey. I will be, yes, and that's mute. Good evening, everyone. That said, well, hello, mute.
So here's the basic setup process to actually use the Nano VNA. Okay, you set up and configure what traces you want on, like how many traces do I want to look at? Maybe I just want to look at SWR, okay, or maybe I just want to look at my S21 parameters or whatever it might be. So tell it how many traces you want on, what channels those traces are on. The channel determines whether you're making a reflection measurement or a transmission measurement for that trace, and then what format those traces are. And then you set up the stimulus frequency range. Now, those two things can be interchanged. You can start off by setting the stimulus and then set and configure the traces and channels. Okay, but usually those are the two first steps that you do. The third step is to run that calibration. Okay, now that I've established the stimulus, I want to run a calibration and then save it. So that now I've got it and I can go back and return and make the measurements. After that, I connect my device and I go and make my measurements. Okay, extract what I want to go look at, do what I'm doing with it, and then I'm essentially done. I can add markers, make some extract some numbers off, things like that. And then if you want to adjust the traces and formats, you can add traces, take them away, things like that. That's all fine. If you go and change the frequency that you're measuring, then you probably want to recalibrate again. Okay, but just changing which traces are turned on or off and what channels they're on, you don't have to rerun a calibration, only really if you change the stimulus or the frequency range. So here's an example of measuring an antenna, for example. So I've got an antenna, right? This really sophisticated antenna connected here to channel 0 or port 1. Okay, and down here along the bottom, this is the frequency range that we're measuring over. In this case, I can see I set a start and stop frequency, 7 to 7.3 megahertz. So this was measuring my dipole antenna here. I had the tuner set up for the phone portion of the 40 meter band. This plot here, okay, so let's look at this. So this plot here, this blue trace is SWR. So we can see here it's channel 0. It's showing SWR 1 per, meaning that this is 1 to 1, 2 to 1, 3 to 1, 4 to 1. Okay. This marker, which I unfortunately didn't move, the marker is sitting way over here. Okay, you can see it's sitting at 7 megahertz. And that marker is showing an SWR of 4.73 to 1 down at the very bottom of the CW portion of the band. Okay, you can see it going all the way down to essentially near 1 to 1 way up here. Okay. The green trace here is on channel 0, so it's a reflection measurement. It's on the Smith chart, so it's essentially showing me complex impedance. And we can see that where this marker is, this is 16 ohms and 822 nanohenries. And as we walk our way through, right at this point in the center, and it's kind of hard to tell that, but right where I'm pointing here in the center is essentially this frequency here, where we've minimized SWR and got the lowest possible best reflection loss or return loss. So this is the reflection coefficient. Okay. Again, reflection coefficient and SWR are mathematically related to each other, so they're both going to give you the dip at the same point. It's often easier to see the location of that dip on a log magnitude reflection coefficient plot as opposed to SWR. It's very easy to kind of see where that point is. It's kind of a little bit shallower on the SWR plot. Okay, and we can tell that is a reflection coefficient because it's on channel 0 and looking at log mag. All right. So let's look at another example measuring a filter. This is actually measuring a low pass filter that I designed for the output of a little Michigan Mighty Mite 75 or 80 meter CW transmitter that I built. And so again, the frequency range down here at the bottom from 1 megahertz to 15 megahertz. The insertion loss, okay, if we look at this blue trace, okay, see that's channel 1 log mag. So channel 1 means that it's my S21 measurement, okay, and the log magnitude of that. So I'm sitting up near 0 dB. This is my pass band, all right. And then at 10 dB per division, I'm 10 dB down, say here, 20 dB down here, 30 dB down here as I walk my way down. I can see marker 1 is sitting way down here at about 10.5 megahertz, about the third harmonic of this 3.58 megahertz transmitter. So I can see my third harmonic is 47 dB down. Okay. The SWR looking into the filter is shown here in the purple trace. Again, channel 0, SWR. I can see it's all down below 2 to 1 until I start rolling the filter off, and then the SWR rockets up, which means that the signal is being reflected off of the input of the filter, by second, third, fourth, fifth harmonic, etc. Okay, is not getting through the filter. See the reflection coefficient. This is another way of looking at the input return loss. I can see that I'm better than 10 dB down, over the passband of the filter, and then the reflection coefficient gets close to 0 dB, meaning I'm reflecting all the energy off the input of the filter when we get up in these higher frequencies. Okay. So then the input impedance, which I really didn't have to plot here, because I left it on just kind of this little curly Q on the circular Smith chart axis here. So let's say I want to measure the length of coax. In this case, we're using the time transform capability of the analyzer, and I'm using channel 0, and I set it to linear instead of log magnitude. So this gives me a linear measurement of the S11, but in this case, because of the time transform, the x-axis is now time. Okay, so it tells me how long it takes for that reflection to come back from the end of the cable, or a discontinuity in the cable or something like that. And if you tell the analyzer what the velocity factor is of your coax, when you put a marker on there, it'll actually tell you the distance. So this was 9.13 meters. So it was like a 21, 22, 23 foot piece of coax that I was measuring here. So that actually showed me, right where that length was. So it measures time in this axis, but then converts that to distance as long as it knows the velocity factor. Now, of course, if we change modes and turn the transform off, we can measure, something like, insertion loss of that coax by connecting it up to the other end and measure insertion loss versus frequency. So as with anything, there's, the good, the bad, and the ugly of the Nano VNA. Okay. So there's some limitations and downsides, right? This thing only costs $60, so it can't be perfect. So there are going to be some limitations. Let's take a look at that. Again, most cases, 101 trace points. So external software like the NanoVNA saver I mentioned can help with that. But otherwise, you've got a pretty granular measurement range. So you want to kind of focus your measurement ranges to be over the specific frequency range of interest to get good resolution. Okay. You don't want to calibrate over the whole HF band and then make measurements just on 17 meters, because you're not going to have enough resolution to see that. So if you're looking even like at a multi-band antenna, you probably want to sweep one band at a time as opposed to sweeping all of the bands. Again, third-party software helps that. Now the output of this, of the Nano VNA, is not a sine wave, right? It's a square wave, all right? And so this is actually what it looks like on a scope. Okay, there's a square wave. Okay, and on the H4, for example, it uses the fundamental, and this is the square wave in the time domain, and this is what that signal looks like in the frequency domain up here. This is the spectrum plot of it. So my fundamental, third harmonic, and fifth harmonic. So on the Nano VNA H and H4, the measuring signals up to 300 megahertz uses the fundamental of the square wave. But when you make measurements from 300 meg to 900 meg, it uses the third harmonic of this square wave. And from 900 meg to 1.5 gig, it uses the fifth harmonic of the square wave. Okay. So this output that I'm showing you right here is a 200 megahertz square wave. It's the same exact signal that's used to measure at 600 meg and at 1 gig, right? Because that's the third harmonic and the fifth harmonic of that square wave. So it's not a pure RF signal generator, okay? It's a square wave generator that's got all this harmonic energy. So you have got to consider whether the device you're measuring is going to have a problem with that, okay? If you're measuring a broadband RF amplifier, for example, you've got to think about the fact that you're supplying it with a signal that is rich in harmonics, and it's not just a pure RF signal. And is that going to pose a problem? Okay. The other problem compared to a true VNA is that the output power is not adjustable. Okay, it's a square wave of essentially a constant amplitude. Okay, And on the H4, that's what I made the measurements on, the fundamental from 50K to 300 meg, it's this 600 millivolt peak to peak square wave that gives you somewhere between 0 and plus 2 dBm, so about a milliwatt to a little over a milliwatt, or close to 2 milliwatts of power at the fundamental, and then a good 10 dB lower than that at the third harmonic, and another approximately 10 dB lower than that again on the fifth harmonic. You can't adjust it. Okay. So again, is this the correct power level for the device you're measuring? If you're measuring something like an antenna or a passive filter or something like that, it doesn't really matter. But again, if you're measuring an active device, like an active filter, or an amplifier or something like that, you've got to start considering, do I have enough signal there to drive that device, or am I driving it too hard? Am I going to drive it into compression or create distortion on my device because of that signal? And is the fact that is a square wave going to be an issue? So these are things you might want to think about if you're going beyond just measuring like a passive device. Okay.
Alan, question?
Yes. Yes, sir.
Yeah, it's Gordon.
Hey, Gordon.
WTTT. Quick question. If I'm a lucky guy who's got an SAA2,
Yeah.
and so I'm thinking that it's probably the seventh harmonic, and again with scaled output, reductions, or
Yep.
do they buffer it? Do you happen to know by any chance?
Well, actually, the SAA2 uses a different synthesizer, and
Okay.
it's still a square wave output in most cases, but it uses a fundamental for all the measurements.
Oh, really?
Yes, at least for the SAA. I've got an SAA2N, and that one I made a measurement on it. It uses the fundamental all the way up.
Okay. Yeah, I like mine, but the only question is I'd love to see an SAA2N with a 4-inch display.
Yeah, well, that's what I have. It's not officially sanctioned by the original developers, so when buying it is not supporting the original developers. I learned later, but I do have. That's the one I have is the SAA-2N, and it actually does have a 4-inch display.
Okay.
So and then those guys are working on a couple of other variants of it now, which is probably worth waiting for to go up a little north of 4 gigahertz. So
good. Thank you,
okay.
sir.
Sure. Again, we talked a little bit earlier about the limited dynamic range at the first harmonic or the fundamental. You're probably talking in the neighborhood of 60 dB. You get up to the highest frequency range, you may be down as low as 40 dB or a little bit less. Some of the newer vert models that we talked about, like the one that Gordon mentioned, the SAA2, they're better in terms of dynamic range, but they're still not going to come close to what some of the professional units get. But again, for $50 to $100, you're getting what you pay, getting a lot more than what you pay for still. The measurement resolution bandwidth is not adjustable in most cases. Some third-party firmware that's out there, some other developers have developed some firmware where you can adjust the resolution bandwidth. But again, it's of somewhat limited utility because of the limited number of measurement points that you have. And of course, there may be some other limitations as well. So, there is some good, bad, and ugly with the Nano VNAs just by their nature. But again, for the money, it's just pretty incredible. So, kind of in summary, I would say that the Nano VNA is probably the RF tool or toy of the year in terms of bang for the buck type of capability. If you're considering an antenna analyzer, the Nano VNA is a nice choice. The downside is that it's not going to be as rugged as like a Rig Expert or something like that, and the display isn't going to work as well in bright sunlight as some of the other things. But these are trade-offs you might be willing to live with for $60. Okay, so really amazing capability for that $50, $60. There's a ton of videos and things like that that are out there to learn how to use it, because there isn't really even a good user manual that's out there. Some very active user groups online to kind of learn more about it and get problem solved and questions answered. And what I found in the US anyway, because of all the various clones that are out there and things like that, you don't know where to buy it from and who to get it from or whatever. Go to a kind of more reputable dealer And the guys at R&L Electronics generally are sourcing them from good places. And I've purchased two devices through them, and they've both been built well, and they look like they're they're of good build quality and that type of thing. So they're good to deal with. So any other questions? Certainly let me know. I can certainly unmute yourself and ask questions. I'll take a peek to see if there was any questions that popped up in the chat room while we were going here. See if I can actually find that here. I might have to stop sharing to look at that. But again, I've got a whole series of videos that I've got on my YouTube channel. I think I've got 7 or 8 videos now. The ones I've done most recently on the Nano VNA. So you can certainly kind of check those things out. And there I kind of walk through some of the step-by-step to how to measure an antenna, how to measure a filter, how to run a calibration, how to apply a port extension, that type of thing. I've got some videos on that stuff. So for that, and see if we got any questions.
Greg, K1UH, how immune is the Nano VNA to extraneous RF that may happen to be, on your bench or that? Is there isolation from stray RF or noise or anything like that?
That's a good question. I think they're generally pretty good, because even though like this guy here is this is the Nano VNA H4. Even though it's a plastic case, inside the channel 1 and channel 2 have got shields soldered on them, and they kind of have to in order to kind of even get to the 40-50 dB dynamic range that we're looking at it with the devices. They kind of have to be pretty well shielded. I personally haven't had it at a high power repeater site or something like that, simply because even though these things are not going to have the dynamic range you need to measure a duplexer. Okay, so I haven't had to bring it into that environment. In terms of how immune they are to RF coming down, like if I'm measuring an antenna that's up and I've got a strong signal coming into that antenna while I'm trying to make the measurements of it, how well is it going to react to that? Probably not great, okay, because again, it's $60, but it all depends on what, like if I'm trying to measure a long wire antenna that might be getting hit really hard by a broadcast AM station or something like that. I don't know that there's enough filtering in the front end of that to knock that down to not cause some problems, okay? So just be cognizant of that. Good question though, Greg, thanks.
I'll just share because I'm a tinker. I'll show you what I put together here. So they show up.
Oh, I see it. Yeah.
These are bandpass filters for field day, 20 meters and 40 meters.
Yeah.
And of course, we've got this little eBay VNA. Problem I ran into is, wiring the toroids. I'm a statistician by training, not an electrical engineer.
Okay.
So trying to learn all this stuff, trying to figure out how to measure this bandpass filter. Greatly appreciate your presentation. I now see I wasn't able to get the toroids measured. I had a grid dip meter from a Silent Key and his oscilloscope, right?
Okay.
And that method didn't work. The VNA did SWR, but I now see that I got to do the through measurement to measure well, I'll probably get the same result, but
the reflection measurement gave you a measurement of how well the filter was matched, probably at the bandpass or in the pass band itself, but didn't necessarily show you how flat the filter was or how much rejection there was, at the frequencies where you're trying to block signals. So using the through measurement will help you with that.
And that'd be a log mag measurement, right?
Yep.
So we'll hook it all up there and got the pigtails. Very good. Thank you.
Sure. Thank you, David. Roger, you got a question?
Yeah, when you're trying to measure the length of a piece of coax, which I haven't tried yet, you have to do the through calibration to do that. I'm guessing you do.
To measure the length, if you're going to be doing it using the transform function, you're only really attaching to one end of the coax. So you only have to do the open load and short calibrations. Okay.
Then you only have to enter the velocity factor and that's it?
Yeah, so the open load and short, and then you enter the velocity factor if you actually want to give it the length. I do have a video on that. It's one of the probably one of the last ones that I did within the last couple of months on my channel that shows you how to go ahead and do that.
Thank you.
Sure.
How does that compare with using the Nano VNA as opposed to a TDR?
In a sense, a TDR actually measures by applying a step or an impulse and measuring the reflection coming back. The Nano VNA does it by measuring essentially the impedance looking into that coax versus frequency and doing an inverse FFT to get to time domain. So they're doing the same thing but approaching it from a different mechanism, but they'll give you the same result.
I'm interested only because I have a TDR, a pretty decent one.
Yeah.
And I got the Nano VNA after you had your presentation with NJARC.
Yeah.
And I got the book and everything. I just haven't dug into it yet, but it would be interesting to compare the TDR with the VNA and see what I get.
Yeah, it would be. I mean, the TDR is probably easier to set up because on the VNA, you've got to think about, the resolution and distance that you can measure is proportional to the frequency range that you measure. So, and there's a relationship there. I go into it in the video a bit more, saying if you kind of have to approximate over what's the longest length that I'm expecting this thing to see, and then you set the frequency appropriate for that to get the best resolution. You're probably going to get better time domain resolution on the TDR than you will with the Nano VNA, but essentially you can get the same measurement.
All right, thank you very much.
Yeah, but if I was me, if I had the choice, if I had both a TDR and a VNA to measure distance to fault or length of a coax, I'd use the TDR. Okay, but if you don't have a TDR, the Nano VNA can do it for you.
Thank you.
Sure. All right. Well, it's a good thing everybody's muted. I didn't get to hear the snores, so that's good.
Hey, one other thing you could do is using the Nano VNA, you could actually determine the velocity factor of an unknown piece of cable.
Yeah.
So
yeah,
you
if you can
flip
measure
the
it,
script the other way around.
Exactly. If you can physically measure the length of it, and then use the TDR to see what length it thinks it is, then you can do the math the other way, like you said, and actually compute what the velocity factor is. That's, again, a good point.
Al, I have one more question. It's kind of semi off topic, but you've done a bazillion videos and they all take different shapes and sizes depending on what you're doing.
Yeah.
And I've seen KE0OG's, how he does his video.
Okay.
But he uses a standard thing. He does the same thing ever the same way, virtually all the time. You have a lot of different formats. And I was wondering if you would, maybe in the future, consider producing a video on the different kinds of presentations you put together and how you do them. The mechanics is kind of a how-to guide, because you're really good at what you do.
No, I appreciate that. Yeah, it's we all have our own styles of doing things, and I try to spend enough time on how to do the video in a way that I get rid of all the fluff. I don't do any of the wanking and wandering like the EV blog guy does. I try to make it all just just good technical content and straight to the meat of it with very little fluff. And then to me, decent audio is important, and having good visuals in terms of whether it's notes or camera placement or things like that. So the thing that I do that's probably more different than a lot of the other folks, especially that Dave Kassler, is that my videos, even if it might be 10 or 15 minutes long, might consist of 40 or 50 different clips that all get clipped together. So each clip becomes, is optimized for that particular thing that I'm saying or showing. Okay. So one thing I'll show here maybe is let me go and share, just in case somebody's not familiar with the channel. Let me bring that up here and share it. This is kind of what they go to the youtube.com/mycallsign will bring you to the channel, and you can see the most recent videos here. If I just bring up the videos list, we can see that from video 313 all the way up to 320 are all about the Nano VNA. So first one is why we need to calibrate, how to sweep in antenna, how to measure a low pass filter, etc. Something else I'll show on the channel here, because I've got 320 videos here. You might say, well, it's kind of hard to find the video that I want. If you go to the channel graphic right here, you can see over on the upper right-hand corner, it says video index file. And if you bring that up, it opens up a PDF file that is an index to every one of the videos that I have. And you can do a simple search to find a topic. This index is arranged numerically from video number 1 all the way down to 320. And then after that is a list that's based on topics. Like here's a list, here's all the videos based on oscilloscopes. Here's the list based on spectrum analyzers or other test equipment, test procedures, circuit construction, basic theory, and components, circuit analysis, ham radio topics, etc. So you can pretty easily find the videos of interest, and every one of these is a hyperlink to bring you to that particular video. So that could be kind of handy. And then on most of the videos, for example, let me just pull one up here. So I know that's got some notes here. If I pull up this one, like say for the Nano VNA, or to how to calibrate it, well, I'll stop it here for a moment. And if you go down below the video where it has a description and you click on show more, there'll always be a link. Anytime I publish notes, there'll be a link that'll bring you to those notes that I used in that video. So, so you have your own copy of the notes that you can go and look at as well. Since I've got this up here, this is that the Nano VNA page, the main page. And you go to the wiki and user group page, and that brings you to this link here. And here there's files that'll bring you to like places where you can find the firmware and things like that. There's a ton of good information. And then the VNA that Gordon mentioned, the SAA2, its official site is this one here, this Nano RFE. Okay. And there's a couple of different variants that are already out there. These are different hardware variants that are out there right now. But then, some information is here on these things as well. So there's different hardware versions. There's a couple of different versions where you can get the different firmwares for each of these things as well. So the information's out there. The links are there. So again, hopefully that'll help you out.
Thank you, Alan.
Sure.
Is this presentation going to be made available to view at a later point?
Yeah, well, I know that they're doing a recording of it, so I'm sure that they'll make the recording available on the club website. But what I can also do is make a PDF copy of the presentation itself, and I'll send that off to the club folks, and they can post that wherever they deem fit for download for anybody in the club.
Alan, I got to thank you for your work here. I was playing around with looking at a linear amplifier and how to test it on a scope, and found a great YouTube, and I'm watching it, and I'm looking at the guy who did it, and it's W2aew, and I thought, oh, that's the guy I'm gonna be watching tonight.
There you go.
Way to go. 2 questions. What do you use for your video editing software, and what is your little avatar with the guy screaming there?
Well, good question. Well, number one, if you're measuring an amplifier, you make sure you properly use some attenuation and things like that to you don't go blasting the daylights out of the VNA. So 2 questions you had. The software I use most often for the majority of my videos is an open source piece of software called Shotcut. Actually, let me minimize this here because it's on my desktop here and I don't remember exactly that's what it's called, but let me just check here. Let's see. Yeah, Shotcut, SHOTCUT. So that's the, let's bring this back up here. Where'd you guys go? All right, let's see. Oh, I minimized y'all, now I can't get you back. Here, let's see. Hello. There we go. I got you back. Okay. So Shotcut is what I use, and it's really nice. It's easy to bring all the clips in, merge them, clip them, size them, do things like that. Some special effects, although I don't do much with special effects.
Thanks,
The other
Alan.
piece, the avatar piece, is actually I did a circuit several years ago that took NTSC composite video and converted it into X, Y, and Z waveforms that would normally drive like an analog CRT, like a television monitor. Okay, and I applied them to the X, Y, and Z inputs of a scope. So I turned my scope into a video monitor, and then took a camera, pointed it at myself, and made that goofy face like I was trapped in the scope, and that was displayed on the scope screen. And I took a picture of it.
So that's a picture of a screen on a oscilloscope.
Yeah. So in fact, let me go back and share my screen here again. If I go back and share, let's see. Let's go back to the web page. In fact, if we go to my channel again, and if we, so my trailer video was actually showing that. So it's actually, you can see live. That's actually, you can see the controls of the scope here. Okay. But if we search for video here, and this is a good place to search for videos as well.
That's awfully clear.
So if I do NTSC, this video right here, number 86, is that circuit. So if you actually want to do it yourself and play with it, if you got a video source like a camera or a VCR that has an NTSC composite video output, you put that into the circuit, you take the X, Y, and Z waveforms, plug them into a scope that can do it, that has X, Y, and Z inputs, and turn the scope into a video monitor.
Holy cow.
So that's how I did it.
Amazing.
It's a simple circuit. It's a super simple circuit. So
mystery solved.
There you go. Well, yeah, you know all my secrets.
Thank you.
All right. Well, with that, hey, I thank you guys for having me. I'm glad you stayed awake for the presentation. Like I said, I'm sure they'll make the Tom and this guys will make the video available to you, and I'll get a PDF copy of the presentation to them to go take a look at as well. So
thank you very much, Alan.
All right. All right.
Thanks again, Alan, for the presentation.
You're welcome. Thank you.
Thanks a lot, Alan.
Thanks
All
for
right.
John.
Thank you from
Yeah,
Tennessee.
Thanks,
All
Alan.
All right.
God bless.
All right. Take care. Take care. Stay safe, everybody.